All right, 3-2, day one. We got our discussion going on polynomials of higher degree, okay? Kind of touched on it in day one, but when we say higher degree, we really mean higher than 2, okay? Technically, if we want to be like real specific with polynomials, they could actually go all the way down to degree 0, where if you had like a horizontal or a vertical line, you could say that's a polynomial of degree 0. And then if you had any type of line, like a diagonal one with a positive or a negative slope, you could say that's degree 1, and then quadratics, we'd mentioned before, are degree 2, okay? But again, lines of any type we don't really think of as polynomials, even though technically they are, okay? We tend to start the discussion at second degree, and now we say higher, we're saying, all right, 3 or higher. As I look ahead to today, it looks pretty typical of what you would expect. I think we'll see 3, 4, and 5, okay? So a graph this is kind of a general property of polynomials. We say it's continuous if it has no breaks, holes, sharp turns, or gaps, okay? Big point to make down here. Polynomials are continuous. They have no breaks. Okay, that would be like right here. That's got a break. Probably some kind of like piecewise function, but you know, just not a polynomial, which is why I'm crossing it out. This looks like kind of a weird looking absolute value one, but it's got a real sharp turn. Polynomials don't do that. This right here looks like a polynomial, okay? Notice it's got a real different shape from a quadratic because that's what we're going to see happen if the degree is higher than 2. No breaks, no holes, no sharp turns, no gaps. It can change directions, right? Unlike a quadratic now, we can see it change directions more than one time. But when they do, it's kind of a nice, gentle turn that looks like a nice curve on the graph. That looks like a polynomial too, right? It's changing directions the whole time, but if we take the degree and make it a lot higher than 2, that can potentially happen. All right, we'll kind of build our way towards producing a couple of sketches. That'll be a bigger focus in day 2, but you can think of this like it's just good properties to know about the graph. Whether your intention is to produce a graph of it or not, the equation would tell you characteristics of the polynomial. Okay, so split these up 1 and 2. Okay, so n is your degree. Notice right here, these first 2 graphs are talking about what's going on if the degree or the power, okay, which we're used to seeing be no higher than 2, because that's what we saw happen with quadratics. If it's higher than that, and it's odd, okay? So we're talking the 2 that you will see quite a bit of, I think you'll see both today, are what if the highest power is 3 or 5? You won't see 7 today, but let's just pretend theoretically that we were. So 3, 5, 7, etc. Okay? You got 2 different possibilities. Okay, this leading term will tell you a lot. This first one right here is if your leading coefficient, right? This is going all off of the first term, right? Hence the leading coefficient test is in terms of like the tails or the end behavior, that coefficient tells you a lot. This first one is saying if A is greater than 0, you would always see that the left tail, the book doesn't use this language, but I like to call them tails. It's like the end behavior. Not all the turns and stuff going on in the middle, but like eventually a polynomial takes off and goes one direction or the other. Okay, and in between it can kind of do some funky stuff, but if n is odd and your leading coefficient is positive, your left tail is going down and your right tail is going to go up. Okay? If you were to switch that and say that a is negative, it would swap. Your left tail is going to increase, your right tail is going to decrease. Okay? Notice the general theme here, though. If n is odd, the tails go opposite directions. That's not a coincidence. That's a property of polynomials that you should know. Okay, the tails go in opposite directions. Let's jump over here. Okay, the only difference now, n is even. So we've seen this with quadratics. That would include 2, right? You'll see 4 today. You won't see 6, but I'll put it on there. But this would continue even if the power was higher than that, 8, 10, 12. We would work with those a lot, but the same property would hold true. Okay, this first one right here is that a is positive. If that's the case, you're going to see both of your tails going up. And just the opposite over here, if a is negative, both tails would go down. Okay? Here it's nice to get back to thinking about quadratics because, they have some, like quadratics have some unique properties, like the quadratic formula. They tend to be easier to factor, which is why we tend to look at them separately, okay? However, they still fit these types of properties, right? We've seen with quadratics that if a, that number in front of the first term, right, what we call the leading coefficient, the number in front of x squared, if it's positive, that quadratic and its graph opens up. If it's negative, it opens down. That's the same as the tails just going in the same direction, okay? So if we made the power higher, like 4 or 6, it would still hold true, okay? You can generalize this if you're talking even powers. The tails go in the same direction. So it's one of the first things, right? When you're looking for that leading coefficient, what is the degree? All right? What is it? Specifically, is it odd or is it even? Because that's going to really change what the graph is going to look like. So let's practice this with a few. All right, just basically describing the left hand and right hand behavior. That's what I've been calling the tails. Okay? I've been calling those the tails. All right, so I look at this, and I'm saying, all right, here's my first term. 2 things I would notice about it. N is 3. A is -1. Okay, those are the 2 parts I would need to see. Now, if I look back at those diagrams I have from up above, I'm not at all concerned about what's going on in the middle, but that looks like the second one. That would be something like that. Okay. Again, the leading coefficient test, as far as like where the zeros are and what's going on with the graph in the middle, it doesn't tell us anything, right? That'll come later on, specifically in the second day of 3.2. We'll get into that, but this, this leading coefficient test tells us some stuff about the polynomial, but it doesn't tell us everything. It's really all about the tails. Okay? So if I were to describe this, I would say left tail is going up. I'm just saying increases. If you had wanted to, you could say goes up and goes down. That's totally fine. Honestly, might even be a better way to say it. Left tail is going up, right tail is going down, okay? Again, zeros, I know nothing at this point. Is it changing directions in between those tails? Yeah, probably. How much and where? No idea. Okay. The leading coefficient test doesn't tell us that. All right, take a look at G. I noticed two things. First off, n is 4. Leading coefficient is 1. Okay? In other words, right? Specifically, it's even. And A is positive, right? According to the leading coefficient test, that's very specifically what I'm looking for, right? Degree is even, A is positive. So if I relate that to those sketches, you'd have something like this. And I could generalize it and say both tails go up. Okay, and I could add over here. You know, specifically what I was looking for. The 3 was odd. And the leading coefficient was negative. Take a look at our last one here. Last one of the slide, not the last one of the day. Didn't mean to get your hopes up there. Though you could probably see the time below and be like, wait a minute, we're not done yet. Not quite yet. All right. Odd. Positive, right? Odd and positive. That looks like the very first one we saw up there, which would mean left tail is going down, right tail is going up. Okay, so there's 3 examples of the kind of the leading coefficient test put into practice. And there it's applied to some different polynomials, right? You got 3 of them there. 3rd degree, 4th degree, 5th degree, which, again, for most of chapter 3, like we'll learn some properties that would go beyond these 3, but those are the 3 we're going to spend most of our time, is 3rd, 4th, and 5th. Okay, right? So the next piece with like seeing some characteristics of polynomials is, right, this leading coefficient test tells us about the tails or the ends. Like, you know, polynomials in either direction, positive and negative, eventually they take off and either keep increasing or decreasing, and that leading coefficient test tells us how that happens. Those gaps in the middle of those little sketches I was drawing, what's going on, right? We need some zeros. Okay, so here's what happens. We need to find some zeros, set it equal to 0, and then we need to factor. And first things first here is you're going to be looking to find some common factors, okay? It's worth noting we'll need some more tools than what we have today, okay? Finding factors of higher degree polynomials, 3rd degree or higher, is tougher than quadratics. Here's the other part, okay? Zeros are still something we're really interested in finding. But if our degree is higher than 2, the quadratic formula doesn't apply. And they're harder to factor, okay? So finding zeros in general, this is going to take some time. We're not going to see it all today because it's a little bit of a different situation than quadratics. Now, when we do this, we still apply what we call the zero factor property. Recall from chapter 2 that says this. If you have two expressions that are being multiplied, okay, and their product is 0, this tells you one of two things. Okay, so when it comes to finding zeros for polynomials, it's a useful little statement for us, or a little property. It really does work nice, and if you think about it, you can convince yourself it's true. Really think about it with numbers, right? Because it applies to more than just numbers. You could put in variables and do some algebra with it, but if you're multiplying two numbers, a times b, and you know their product equals 0, either a or b has to be 0. There's no other way about it, right? If both numbers are not 0, when you multiply them, you're going to get an answer that's not 0. So one of them's got to be 0. Okay? The other thing we need to be aware of is polynomials can switch from increasing to decreasing. Okay? That's going to come up. Follows a pretty simple formula. Okay? We've actually seen it in the two cases that we've seen polynomials. Again, we don't think of lines as being polynomials, but they are. So if it's a first degree polynomial, that's more what a line is, n minus 1 would be 0, which would tell you lines can't change directions. They could switch directions 0 times. Okay? If you think about all the graphing we did with lines, I think you could convince yourself easily that, yeah, that's like a really fundamental characteristic of linear functions, is they don't change directions. Their slope is positive or negative, and it never switches. Now, think of quadratics. Here's what the formula is saying, that if your degree was 2, that's what a quadratic is, that polynomial can switch directions 1 time. You'll see this pattern continue, that if you have a third degree, it's a weird way to say it. 2 switches, probably better to say it that it could switch twice, but whatever. You get the idea. And if you had a fourth degree, it could switch from being an increasing function to a decreasing, right? So here's a little sketch, right? That would be like a quadratic. Third degree, you could have something like that. Fourth, you could have something like that, where if you look at kind of those intervals where it's increasing to decreasing, it changes 3 times. Okay, that would continue on and on as you made the degree higher. Okay? So what we're after right now is we're trying to take, not just the tails, which the leading coefficient test helped us out, but what's going on in between, right? We're trying to figure that out. Where are the zeros? Where does this go from switching from increasing to decreasing and that kind of thing, okay? So for now, to find zeros, we'll really need to focus on looking at some common factors. Now, it's not going to come up here, but just it's worth noting. If I applied the leading coefficient test, I would see the degree is even. That tells me the tails are going in the same direction. And then the leading coefficient of -2 is odd. Okay? So they would both be going down. It looks as though those two terms both have -2x squared in common. When I take that out of the first term, all I have left is x squared. When I take it out of the second term, all I have left is -1. Okay? If you're having a hard time seeing that, sometimes it's helpful to look at the opposite, right? If you were to distribute the -2x squared, you should get back to the original expression that you started with. Okay? Now I get this part down to a quadratic, so x squared minus 1 will factor nicely into that. Your zero factor property says if you want to find zeros, take each of those factors, set them equal to 0 and solve them, right? This would give you a solution of x equals 0. Here would be x equals -1, and there x equals 1, okay? Now I saw it was 4th degree, so I'm kind of making a note down here. Could change direction how many times? Three times, okay? Technically speaking, we're not going to get real deep into this idea. Could be fewer, quite honestly. It could be fewer than that. Can't be more, right? This is a 4th degree polynomial, so one thing that is not possible is for it to change direction 4 or more times. Not going to happen. At most 3, okay? Really good example right here of how we're going to find zeros. Okay, this is a little bit incomplete, right? This whole common factoring that we're looking for is just to get us started. We'll need more. And in section 3, we'll get some more tools that we can find zeros for polynomials like this. All right, so you're going to run into this concept of repeated zeros. Okay, I'm going to start you with a quadratic. I know that's not a higher degree polynomial, but whatever, it's fine. It's a good one to look at. I would need 2 factors of 9 that add up to -6. I can already see it happen right there, that it's the same factor. So this could be written like that, okay? If you see that happen, if you're finding factors and finding zeros and you see it as 2 of the same, okay, the 0 is at x equals 3. Okay, but from right here, we'd say that 0 has a multiplicity of 2, okay? This gets really significant because something happens that's a little bit unique at that spot, okay? Here would be a little graph of the quadratic. To make this graph, I'm not doing anything fancy. I'm not writing out a table of values, but that's all I'm doing, is I'm starting at 3 and then putting in 2 and 4 and so on. Which if you wanted to, you could use your other methods to get a quadratic. Find its vertex and all that. Okay. So notice here, this quadratic, it has a 0, but it just comes down to the x-axis, and it just touches, and it goes the other way, right? What's going on in this example is property number 2, okay? You may also use this term. But we'd say at that 0, the graph bounces, okay? It just comes down. There is a 0 right there, but normally what we expect is what we're going to see in property number 1, where the graph crosses, and it goes from a positive graph to a negative. If you have a factor that has a multiplicity that's even, the most common one you're going to see is a multiplicity of 2, okay? A factor that's squared that basically leads you to 2 factors that give you the same 0. At that 0, you're going to be talking about a graph that bounces. Just going to touch the axis, and then it's going to go back off in the opposite direction. To contrast that over here, okay, this has a 0 at -2. Its multiplicity is odd. So it's like you've got 3 of the same 0. If it's odd, it's going to cross, okay? Now for this one, I'll actually make a little table. If you put in -2, you'd get 1. Put in -3, you get -1. Take some time if you wanted to verify those 5 points, but just you're plugging in x values to get y values. All right, so right here, here's -2, 0. negative 1, 1, negative 3, negative 1. And the other points are actually too high. Those are the only three that fit. But this is a third degree, right? So notice it's got those tails going in opposite directions. But at that 0 of negative 2, I would say the graph crosses, right? You hit a 0, and it before negative 2, you had a bunch of y values that were negative, and then at negative 2, it switches to a positive graph, right? Really nice to just step back here and contrast those two. Really nice to contrast those two. Okay, the multiplicity is even, right? Again, the two most common scenarios you would see is that if the multiplicity is 2, you've got a bouncer. Now, in the second one, the multiplicity was 3. That's odd. But the most common one you'll see is a multiplicity of 1, right? On the example we just did, you had 3 zeros, okay? 2 of them had a multiplicity of 1, 1 and negative 1, and then at x equals 0, it had a multiplicity of 2. Okay, so with this whole odd and even, you're usually looking for multiplicities or those powers of 1 or of 2. Once in a while, you might see a 3, but that's usually what you're looking for. Again, you're probably going to have zeros that cross. That's going to be the more common scenario. But if you see a multiplicity of 2, that needs to register that at that 0, we're not crossing the axis. We're just touching it and bouncing off.